All right. So welcome again. All right. For persons who have not seen the topic, welcome. All right. For persons who have seen it before, welcome again to the first row transition metals. Now, the first row transition metals are very interesting elements to me. All right. They are some of the most satisfying elements that I see on the periodic table come from this period 4, right? And period 6 as well. But we're looking at period 4 here when we talk about the first row transition metals, right? We're talking about the elements that exist between group 3 and group 13, I believe. Right, so we're looking at the elements that exist between those two areas. All right, so let me just see in the chat how many persons have gone through this topic already. Just let me know if you've done it before, because as usual I'm going to be asking questions. All right, not seeing anyone. No one has done this topic before. Interesting. All right, so let us begin. Who are the transition metals? Now, as we were saying, the transition metals that we're looking at, right, are between group, well, technically it's between group 2 and group 13. So it starts from group 3 going all the way to around group 12, right? That's a basic understanding of what we define as transition elements at this level in chemistry, right? And they are found within the D block, right? So these are our D block elements that we're speaking to. Right, so many of these metals are characterized by their ability to form different types of compounds with variable oxidation states, exhibit different types of complex ion formation, display colored compounds, all of these different things. And they differ from regular metals, our alkaline metals and our alkaline earth metals, as well as our semiconductors and our metallic substances within group 13 and group 14, as well as group 15. They differ from those as it relates to their high melting points, boiling points, their hardness, their density, their conductivity, their magnetism. All of these things kind of make these D block elements a little bit different from the other metals that we've spoke about before. And we interact with transition metals on a daily basis, right? So many of our most notable types of transition metals could be our chromium, our manganese, our iron, cobalt, gold, platinum, mercury, right? I'm not sure if anybody looked at something like zirconium or hafnium, right? But all of these different elements here, right, are what we call transition elements in a sense, right? But we're gonna really look at why zinc itself is not really grouped in, right? Based on its characteristics and the fact that, well, based on the characteristics and the definition of a transition metal in and of itself. All right, I don't think the information is in the slide, but we'll discuss it. Okay. So the characteristics of our transition elements, right? As I said, these elements are truly amazing, right? So let's have a look at this. These transition elements have varying oxidation numbers, right? Varying oxidation states. As opposed to our calcium that possesses a stable oxidation state of 2 plus, and we see it as 2 plus forever and ever, amen, right? Majority of the other metals within the D block, right, would actually possess more oxidation states that are stable, multiple oxidation states that are stable, right? So transition metals can exhibit a range of oxidation states due to their ability to lose electrons from both the outermost s orbital and the d orbitals. This flexibility allows, right, them to form various compounds with different chemical properties. All right, so this is usually speaking to a type of valence electron effect, right? There's a valence electron effect that we speak about at a level higher than this chemistry that does contribute to the formation of various oxidation states within these metals, right? But that's one of the main defining characteristics of these types of metals in the D block. All right, so if you're looking at this chart here, which I think is one of the better ones, right, we can see the fact that all of these metals can form multiple positive and negative oxidation states, right? And the ones that are highlighted are bold, right, are the ones that are most stable, right, are the ones that are generally stable. So for example, scandium 3 plus is much more abundant than scandium 1 plus and 2 plus, right? So that's what it's really speaking about. Manganese, we see that manganese has a much more stable oxidation states and or ions, because you know that this does speak to ions. One of the greater rules that we speak about within oxidation state is that the oxidation state is equivalent to the charge and the ion of a singular element coming from fourth form chemistry, right? So manganese 2 plus manganese 4 plus manganese 7 plus, or plus 7 rather, right, would actually be the most stable or most common forms of manganese that we find, right? Iron 2 plus and 3 plus are really abundant, but we also have 6 plus, right? Cobalt, nickel, copper, zinc, right, all tend to have stable 2 plus, right? So you can look at these different types of stuff and the fact that they have varying oxidation states. And now notice how zinc itself, right, as the least variable oxidation states, right, that is in agreement with its metallic characteristics. All right, so we can note that as well. So as we go through, we can note that zinc really has the least amount of well, it really appears the least transition like, right? And there's a reason why we don't count zinc as a transition metal, even though it is present within the period and even though it's present within group 12. All right, so if there are any questions or concerns, please do not be afraid to ask, right? But I'll just move through because there is a lot of information to cover. All right. This is also a table showing the rarity or the abundance of these different oxidation states present of the different compounds from group 3 to group 12. All right, in period 4. So you can note that as well. All right. So we have so this table is just an entire summary. So when you get the slides, you can actually go through it. Okay. So complex formation, this is another thing that our transition elements tend to do. They tend to form complexes, right? And these complexes tend to be formed from a central metal ion, which is surrounded by ligands, molecules or ions known as ligands, right? And in a separate session, we're going to speak about ligand exchange specifically with the interaction of iron and EDTA. We're going to look at that specifically. I didn't want to put all of the information into this because we must have specific treatment to ligands, right? So the flexibility of d orbitals allows transition metals to coordinate with varying amounts of ligands and varying types of ligands, leading to intricate geometries, which we will discuss in a specific ligand session. All right. So the formation of these complexes. All right. Colored compounds as well are transition metals are known for different types of colored compounds. For example, we're used to our permanganate, we're used to our dichromate, we're used to our copper sulfate, we're used to our cobalt chloride. We're used to all of these different things. We're used to seeing our ferric iron oxide has iron 3 plus, which is red. Hemoglobin has iron 3 plus, which is red, right? We know that these compounds, these elements form different types of colored species, right? So it's something that we've known already, but we're just looking at it in a little bit more depth, okay? Right, and we're gonna look at how they form these colored compounds and what really affects the colors, right, that are displayed by these different substances. All right. They also display some amount of catalytic activity, right? So transition metals and their compounds often act as catalysts in reactions, right? So this is because they can lend and take electrons easily, allowing for the facilitation, right? Allowing them to facilitate various chemical processes without being consumed. I think my brain just lagged a while ago. So that's what's happening here. So you know what catalysts are. They create an alternate pathway in the chemical reaction without being used up itself. And this is an example using that you looking at the Haber cycle, right? Or the Haber process rather. Right? This is an example. Right, so because of these d orbitals, and notice that these d block elements all of its characteristics is because of its d block, right? So almost every single characteristic answer is d block, all right? Because it's in the d block, or the answer is it's d orbitals. But we must understand what specifically about the d orbitals influences these different types of characteristics. Okay, all right. So magnetic properties as well, right? So transition metals exhibit different types of magnetism due to the presence of unpaired electrons in the d orbitals. So you have paramagnetism, ferromagnetism, and metamagnetism, right? So paramagnetism usually speaks to the fact that, well, usually it gives materials this characteristic for them to be weakly attracted to magnetic fields because of the unpaired electrons. Notice that our elements that have unpaired electrons tend to be mostly paramagnetic. This property is lost when the field is removed. Therefore, we can induce magnetism here if it is plunged into a field with a changing magnetic moment, right? But it is not magnetic otherwise. We also have ferromagnetism, a strong attraction to magnetic fields due to domains of aligned magnetic dipoles. We tend to see this in elements such as iron, cobalt, and nickel, right? We know that iron, when we look at iron filings and magnets and stuff like that, we know that iron is strongly attracted to magnets, and this is because of these characteristics seen here, all right? We also have metamagnetism, a phenomenon where certain metals can become magnetic in the presence of a magnetic field. So we see induced magnetism. They are not intrinsically magnetic, right, or ferromagnetic in any type of way, right? But their magnetism can be induced, right? So for the persons doing chemistry who should be doing physics as well, this information shouldn't be too alien to you, right? So that should be fine. All right. So paramagnetism, they're innately magnetic but weakly so. Ferromagnetism, right? Innately magnetic but strongly, right? And metamagnetism, which is not innately magnetic but can be induced. Its magnetism can be induced. All right. So we looked at these stuff. All right. These things are covered in your syllabus. All right. So we need to remember them. So for the characteristics that the syllabus outlines, we must outline the oxidation numbers, the variant oxidation numbers, complex formation, colored compounds, catalytic activity, and the magnetic properties, right? And all of that is in objective 5.2, which we just covered. Moving on to objective, well, these are just the examples of paramagnetic substances, right? So these are the paramagnetic transition metals that we can see here. Here are the ferromagnetic transition metals, right, as examples here. And here are the metamagnetic metals. So iron-rich alloys, right, tend to be metamagnetic, right? So metamagnetism isn't something that is generally displayed by a metal itself, right, but a mixture, so a metal compound or an alloy, right? So examples are here. Majority of our transition metals are paramagnetic because majority of our transition metals, right, do have unfilled d orbitals, and that is one of the main definitions of transition metals. Transition metals tend to have unfilled d orbitals, right? So please remember that at all costs. If you don't remember anything else about the definition of transition metals, please note that they do have unpaired or unfilled d orbitals rather, right? So unfilled rather than unpaired. Okay, so transition metals contain this unfilled d orbital, right? And that would lead for some of the energies to be paired, some of them are not paired, right? And that would lend to different types of magnetism displayed by these metals and their compounds. All right, so that is really objective 5.2 there. Are there any questions, concerns so far? Oh, and just to state, other elements across the periodic table also display magnetism. For example, oxygen is paramagnetic. Go ahead. Oh, you're saying that there are no questions? All right. So as I was saying again, so other elements are magnetic as well. For example, oxygen, right? Oxygen at a low temperature and high density. Oxygen's color is blue. So if we put oxygen, right, between strong magnets, we can see that it is paramagnetic, right? And if oxygen is paramagnetic, what does that mean? What does that mean for its interaction with a magnet? That's a question to you guys, by the way.
It's weakly attracted to it.
Lovely. Oxygen is weakly attracted to it. All right, but that's when it's really dense and really cold, right? Cold enough for it to see the blue color. All right. All right, so lovely. So moving on to objective 5.3, right? Which we will now discriminate against calcium. I view this as somewhat rude, right? We're gonna look at the the transition metals versus calcium, right? This should say trade. Oh, the trial, right? This should say trial, right? So it's basically like a type of we're going to be looking at transition metals and how they're different from calcium and why we're doing this. Right? Why are we doing this? This is because calcium is also a metal. Calcium is also in period 4. Calcium is right beside of scandium, but it's different from the transition metals. We're looking at how calcium as an S block metal compares to the other transition elements, which are D block metals. All right. So before I continue, is everybody fine so far? Drop a 1 in the chat if you're following, everything is clear, and we're ready to move on. All right. Everything seems fine thus far. Okay. So the melting point, we start here as the syllabus describes. The melting point we must look at, right? So transition metals generally have high melting points due to the strong metallic bonding influenced by the the d electrons, right? Ability to delocalize, right? Within the metal lattice, right? This delocalization leads to a stronger bonding structure, right? We know that metallic bonds are characterized by delocalized electrons. Fine. Calcium now is an S block element, and calcium has a relatively low melting point compared to transition elements. This is what? Why is this, right? This is because there are fewer electrons available for their delocalization. That makes sense, right? If metallic strength is based on the amount of electrons delocalized, then calcium can only give 2, while things like iron and chromium can give around, 4, 5, 6, right, electrons, right, per element, right? Which would mean that if calcium can give 1 mole of electron, right, some transition elements can give 6 times the amount of moles of electrons that calcium can give. Therefore, the melting point and boiling points of our transition elements, right, will be higher than that of calcium, right? Because of the fact that they have way more delocalization within their d orbitals and way more electrons to contribute to the lattice. Makes sense? But if we notice zinc here, right? Zinc is here just, ruining the entire trend. Manganese also has an issue, but we're not really, the syllabus doesn't ask us to really investigate that. But I'm targeting zinc here, right? So look at how zinc has lower melting point and boiling point than that of calcium. One of these reasons is because of the zinc's d electrons, right, are not as low delocalized as calcium's, right? And zinc doesn't actually have unpaired or an unfilled d orbital. It has a filled d orbital, right? So these electrons are held more strongly, right, than the other transition elements. And this is one of the reasons why we keep on looking at zinc and asking why zinc doesn't really show as a transition element compared to its other members in the same period, right? So each time we look at these characteristics, let's have a look at zinc and look at in which categories does zinc stand out or zinc shows poor transition element characteristics. All right. So one of the main characteristics is that we have a high melting point and boiling point. We can have a transition metal which has a lower boiling point and melting point than calcium, which is not a transition element. Right? It just sticks out like a sore thumb. All right. Density now. right? If we look at the density of these elements, transition elements generally dense, owing to their compact atomic structure and the involvement of d orbitals in bonding, which creates a denser lattice, right? So the delocalization of the d orbitals, right, lending to the stronger metallic lattice, right, would contribute to their density, along with the fact that they have continuously, right, higher positive charge, nuclear charge continues to increase as we go across a period, and we've looked at that in module 1. All right, so let's have a look at what's the difference now. What does calcium have now? Calcium has a lower density compared to most transition metals. This is partly because calcium's atomic structure is less compact and it has fewer electrons contributing to bonding. It has fewer. So calcium tends to be a bit larger than the other ones, and we're going to look at that in ionic and atomic radius, right? Radii rather. All right. So if you want to remember this, please note that you can cut calcium with a knife, and you can cut potassium with a butter knife, right? With a plastic knife at that, if you press hard enough. But you can't cut copper with a knife, right? Copper is way more dense than that of calcium. Same thing with titanium and chromium and iron, way more dense than calcium, right? So note how the transition elements tend to be much denser than that of calcium, an S block element. Are you guys following? Hoping that everybody's
Yes, sir,
following.
but you lost me at the trend, how it was zinc that you said spoiled the whole trend with
With
melting point. Can you please go over the explanation as to why? And it's zinc and another one. Which other one is it?
zinc and manganese.
Okay.
All right. So let me just.
Oh,
Oh, go ahead.
okay, go ahead. Go ahead.
All right. Let me
You can
just
go ahead.
complete this. All right, and then we'll go back to that. All right. So let's continue with this, hoping that everybody can see here, right? This is also density kind of goes hand in hand with the atomic radii, right? So based on the involvement of the d electrons right here, the lattices right are held much stronger, right? As well as the increase in nuclear charge as we go across the period, the electrons are held much closer, right? So they tend to be more compact as we go across the period, and it tends to fall off as we enter into the realm of metalloids and non-metals, right? Because those are different, right? As you guys will look at in other parts of module 3, right? But this is the main difference between the density of these elements, right, compared to that of calcium, because majority of the other elements that are outside of the D block, right, they tend to be brittle like non-metals, right, or soft like metals, right? But within the D block, right, we tend to have really dense metals, all right? So going back to this, just to answer her question, right? The strong metallic bonds between the atoms, right? If we look at the strong metallic bonds between the atoms, right, that lends to the increase in the amount of energy required to melt or to boil, right? Increases latent heat, right? And the energy for ionization, etc. Right? We're gonna look at first ionization energy as it goes across, right? But for zinc specifically, I did speak to the fact that all the electrons are paired. It's filled, right? Let me see if I can find that diagram. That diagram is somewhere here. Okay, let's look at. Well, I went too far? Yes, I did. So let's look at this. Zinc here, all the electrons are paired. And thus, majority of them won't participate in metallic bonding. Right? So the lack of participation of zinc's electrons lends to the fact that its melting point is going to be much lower than the other elements, right? Than the other transition elements in this first row. And the fact that since, right, it is so stable in this state and all electrons are paired, right, it will be even lower than calcium, which electrons can participate, but zinc's electrons cannot. And this is one of the reasons why we keep on pushing zinc away, and asking why zinc always breaks a trend, and we don't generally include zinc as a transition element, right? Because majority of transition elements, as you will see, all of them that contains the characteristics and follows trends have unpaired electrons. Zinc does not. Therefore, zinc is not often called as a transition element. Does that make more sense? For the person who asked the question?
Yes, sir.
All right, lovely. If there are any more questions, please ask. All right, atomic radius. No, transition metals, the atomic radius of the transition metals tend to be smaller than the S block elements. We know that atomic radius increases as we go across the periodic table. Therefore, this shouldn't be an issue. Right? This is due to the greater effective nuclear charges Z effective. Right? You guys will learn how to calculate that at a higher level of chemistry, right? Which pulls the electrons closer to the nucleus, resulting to a more compact atomic structure, right? And notice as the atomic radius decreases, right, the density increases. So it's relational, right? It's not like directly proportional. It's not line of best fit relational, but they do relate to each other. All right. Calcium, now being an S-block element, generally has a large atomic radius due to the lower effective nuclear charge. Calcium's charge is plus 20. When you look at something like an iron at 26, right? And looking at these different elements like titanium at around 22, right? You can note that these will have a larger atomic charge, right? Not atomic charge, rather, nuclear charge. All right. So notice that they will have higher charges due to that, and those higher charges will drag the electrons closer together, reducing the spread of electrons, reducing the atomic radius. Hopefully that makes sense. Because if you do have the module 1 lock, module 3 is proper help. Right? So you need to go back and get those concepts. Go ahead.
I think I saw somewhere where they were saying that it's mainly because for the S and the P orbitals, they have a better ability of shielding than the
Mm-hmm.
D orbital. So that is why then you would have the atomic radii decreasing, because when you have the D orbital, it's going to reduce, well, it's going to increase the whole effect of the nuclear charge, and then it's going to attract the electrons and create a stronger electrostatic force, something of that
Lovely.
nature.
Exactly. Lovely. Thank you for that. Right? It's a part of the inert pair effect. Right? It's a part of the inert pair effect as it relates to the fact why our large complex d orbitals, right, lack the shielding capacity of closer, more compact orbitals like the S and P orbital. It's a part of that as well, and that's a lovely explanation. Thank you for that. All right. So that seems like everything is fine there. Let's continue. Ionic radius, right? Our ionic radius will follow the same trends as our atomic radius, because we know that ionic radius, it just speaks to the fact that after the element is ionized, right, what is its size, right? So transition metals typically have smaller ionic radii, no, to their compact electron configuration, and loss of the s electrons followed by the d electrons in their cations, leading to a more compact structure, right? So yeah, so it's leading to that more compact structure, right? And it's a part of the inert pair effect as well, as we reduce the shielding capability of the smaller orbitals. So we actually bring all electrons left, right? After some electrons are lost, because electrons are lost from metals, right? After they ionize, right? The nuclear charge itself will become much more effective or much more stronger, right? Compared to when all electrons are present on the molecule, right? So it's gonna have a way more compact structure, right? And it's a little bit different from calcium when it's ionized, right? Because when calcium really only loses 2 electrons, resulting in a relatively large ionic radius, right? So one of the important things to note is that when we tend to speak about two elements, let's say element A and B, If element A has a large atomic radius, its ionic radius is most likely larger as well, right? But when you start to move at larger distances across the periodic table, some ionic radii may match up, right? But what we're looking at here is just generally the trend. We're not gonna look at those type of stuff, but the trend itself, right? The trend of ionic radius and atomic radius follows each other. So just note that. If you know one, you know the other. The first ionization energy now, and we know what ionization energy is. Please recount it. Somebody please give me the definition.
It is the energy required to remove an electron from an atom.
A more fleshed out definition? Could somebody offer something to add on to that? That's a lovely definition, I know. Can we add on to that? Go ahead. Nobody would like to add? Go ahead.
So the amount of energy required to remove one mole of electrons from a gaseous atom of a molecule.
Alright, that's interesting. Alright, let's fix it up a little bit, right? So it's the amount of energy required, as we stated, to remove 1 mole of electrons from 1 mole of gaseous atoms. That's what ionization energy is, right? So just remember the 1 mole of gaseous atoms at the end. Because if you remove 1 mole of electrons from one atom, I'm wondering where that atom gets so many electrons. Alright, but if you get what I'm saying, right? That's generally it. So the transition metals generally have a higher first ionization energy, reflecting the energy required to remove the outer electron. Alright, so this is due to the effective nuclear charge as well. When you're looking at trends across any period, the amount of protons existing on the element does have a huge impact, right, on the trend as we go across. So we know that nuclear charge is increasing. Calcium is 20, then scandium is 21, titanium is 22, vanadium is 23 as we go across. The atomic number increases, right? So that will have a change in their ionization energy, the first ionization energy, right? So we're looking at calcium now. Calcium is gonna be at 20, right? It's gonna have a lower first ionization energy than all the other transition elements, right? As we go to the metalloids, we have a drop off at gallium and then start surging back up. But we're not looking at gallium. That is a metalloid, not in our transition elements, right? So we can look at that. And usually it's due to the effective nuclear charge and the reduced electron repulsion, right? You guys would have looked at that as well in ionization energy for module 1, okay? So let's continue. Conductivity now. Transition metals, right, tend to be excellent conductors, right, of heat and electricity due to the high mobility of their delocalized electrons, right? So delocalized electrons are important for the melting point, boiling point, and the conductivity, whether it be thermal conductivity or electrical conductivity. Now, calcium, no, while calcium is a good conductor, its conductivity is generally lower, and this is because they have less electrons to contribute to the lattice. Makes sense. Now, looking at the chart, the graph here now, copper is the best conductor of all of period 4, right? And guess what's even better? Gold. Right, so these elements, these transition elements have wonderful conductivity, and this is why we tend to use copper in wires and stuff like that, which would require high conductivity for. We use it in electrochemical cells as well. We use copper as the sometimes we use copper as the wire if we're looking at things that are not more reactive than copper, but generally we can use platinum for more reactive substances. But in this case, copper has the highest electrical conductivity of all the elements in period 4. All right, and we can note that. Now, calcium has a generally better conductivity than a good amount of the elements here, right? And we could start to explain that, but that is not required in our syllabus, right? This is what pains me about CAPE, because there are a lot of things that we look at and we're like, the syllabus not explain this. right? But we're not required to look at it in the syllabus. But generally, due to the theory states that the conductivity of scandium, titanium, vanadium, chromium, manganese, and iron, as well as cobalt and nickel, is gonna be higher than calcium. But that is flawed, and that is what I'm saying. That at higher levels of chemistry, will now actually look into these differences and start to discuss why these things are different. But at this level, we just need to know the trends. Okay? So don't be flustered, but we need to know the trends. Alright? The theoretical trends. Experimentally can be different, but theoretically, that is the trend. Alright? Transition elements versus calcium. This is a summary, generally, right, of everything. Transition metals usually have a higher melting point compared to S-block elements, such like calcium. Transition elements are typically denser than S-block elements like calcium. Transition metals have smaller atomic radii as well as smaller ionic radii compared to an S-block element like calcium. The transition metals typically have a higher first ionization energies than S-block elements like calcium, and transition element metals generally exhibit higher conductivity. And there's a reason why I put generally there, because not all of them. I didn't put typically, but generally. Because we looked at the fact that here calcium is actually have more conductivity than some, right? So I just put generally, right? They have a higher conductivity compared to S-block elements like calcium. Alright. So this is just the entire thing. And all of this would have been objective 5.3, which speaks to discuss qualitatively the properties of transition elements when compared to those of calcium as a typical S-block element. So that entire objective has been discussed. All right, are there any questions or concerns? All right, hearing none. For these trends, right, there is a relatively small difference between the melting points, density, atomic radii, and etc. between these elements, right? Because of their increasing ionic radii and their slightly increasing nuclear charge, right? These elements tend to be really, really similar, right, atomically. So there's not usually huge increases, right? For example, in first ionization energy, there's not really huge increases between each transition element, right? So these changes tend to be relatively small compared to when we end the group and end the D block and head into the P block or S block elements, right? So within the D block, the changes as we go across period tend to be really, really small, right? That's one thing that we tend to look at. Obviously, copper tends to break everything when it comes to conductivity, right? But just some stuff to just keep in mind, all right? Electronic configurations now. We would have looked at these in module 1, how to write the electronic configuration of a substance, right? Specifically the shorthand form where we write the noble gas core as it relates to the valence electrons, right? So everybody knows how to do this, right? Can you guys please let me know, right? Drop a 1 in the chat if you know how to write electronic configuration of substances. You guys need to know how to do this, right? So if you end up not typing the one and you don't know, you need to fix it. Because a good amount of times on paper tools, they just ask you, oh, so what's the electronic configuration of copper 3 plus? Are you going to tell me that you're going to give away the marks? That don't make no sense. Alright? So you need to learn how to do this if you haven't already. Alright, so we can note the differences here. We note that for majority of this group, or of this period rather, or this group of elements, let's say that, right, we have a field 4s orbital. But notice that chromium and copper doesn't have field 4s orbitals. Note that chromium and copper don't have field 4s orbitals. We'll get to why that is, right? All of the elements, right, have some amount of unpaired orbital, whether it be the 3d and or the 4s, right? But zinc has all paired, and zinc is all filled, right? Note that copper's d orbital is also all filled, right? But the other d orbitals up from scandium to nickel, right, are not all filled. Right, so what this is basically doing is using your eyes to look at what's happening with the table, right? What's happening with the information? What do you notice? What are the differences, right? There's a reason why the valence electrons for chromium and copper are in red, because the force only has one electron on it, right? So you guys need to know these differences. They are very, very important. All right. So, are there any questions or concerns before we move on?
Sorry, can
Questions.
Okay, go ahead. Upon the
Um,
question.
as it relates to transition elements, isn't the d orbital supposed to come before the 4s orbital?
Okay, so as it relates to notation, some institutions tend to write it as 4S then 3D, but they do feel right a little bit differently.
Yes, sir, I know the 4s fill first, but as it relates to which one is stronger,
Mm-hmm.
the 3d is supposed to come before the 4s as it relates to d blocks elements. Or so I
Okay.
was taught.
No, that is completely true, right? As I was saying, right, the notation, some people tend to naturally write the 4S before the 3D because 4S is filled before 3D, right? But the general thing is to write your 3D before your 4S, right? It's fine, right? And we generally write 3D before 4S for K. Okay? It's because the trend is 1S, 2S, 2P, 3S, 3P, 3D, right? 4S, 4P, that would be 4S, 4P, 4D, 4F, right? Going up, right? So they will just follow that trend. But how we do it, because we know that 3D is filled before 3D, right? Has some differences with the 4S. We tend to put the 3D before the 4S, right? Um, so that's how we generally do it, all right? But you guys should know everything about this already as it relates to writing your electron configuration, all right? So looking at this now, we'll put the 3D before the 4S here, but here we have the 4S before the 3D because they fill differently, so they put the 4S before the 3D here. But this is how we write it in K, all right? Now you need to know your atomic numbers for your elements going up to the number 30. Alright, so at C could stop at 20, at K could go to 30. Alright, just 10 more, shouldn't be a problem. Memorize them, know them well. Not because you might get a periodic table means you're not supposed to memorize them. Alright, everything should be fine here. For the element itself, with the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, that is the element argon, right? And we can just write an argon complex and argon in square brackets, and then we write the 3d and the 4s, right? Should be fine. Now, we know that there are differences in how the 3d and 4s are filled. Now, how does these differences appear? The order in which electrons fill atomic orbitals and the way they are lost during ionization in transition elements can be a source of confusion. The seeming contradiction between these two processes has to do with electronic configuration, stability, and orbital energy levels. Right? So have a look at this. The filling order 4S before 3D. Aufbau's principle. We know what Aufbau principle states. It states that electrons fill orbitals from lower to higher energies, right? Because you guys should have looked at Aufbau's principle and the Pauli exclusion principle in module 1. Alright? The neutral atoms, in neutral atoms, the 4s orbital is filled before the 3d orbitals because at that stage, the 4s orbitals are lower energy than the 3d. Electron screening and shielding now has something to do with it. Electrons in the 4s orbital experience less electron-electron pair repulsion, right? Not electron pair, rather, electron-electron repulsion, and more effective shielding from the nucleus, making the 4s lower in energy when an atom is in its neutral state. So this leads to the 4s orbital being filled first, right? So note, it has less electron-electron repulsion, so electrons won't be fighting for space and be repelling each other, right, electrostatically as much as the orbitals, right? And 4s orbitals have more interaction, right, as it relates to the nucleus, right? So they're more strongly held, right, within the neutral state of an atom, right? Therefore, the 4s orbitals tend to be filled first because they're at a lower energy. All right. So that those are the reasons why we fill the 4s before the 3D. All right. So you guys should be able to write electronic configurations, right? Therefore, applies a little activity. If you want to do them, that's fine, right? If you want to send the answers to the group, that should be fine as well, right? But this should be something that everybody can do. Any questions? All right. And the reason why copper and chromium have unfilled s orbitals is because of it's really about stability in a sense, right? Because when you look at the energies between the 4D and the 4s, they're not as recognizable within chromium and copper, right? So this anomaly tends to arise, right? And this is because they don't follow the off-bar principle. They're a bit different. So they don't follow the off-bar principle, right? Where we rearrange electrons as we increase stability, right? But they're different to this, right? So it explains why the 4s orbital is not filled, but we start adding into d orbitals because the change in energy is a little bit different within these elements, right? Yet again, it is something that is not explained fully at this level. All right, because I'm gonna need to introduce different terms and stuff and work our way up to why it's like this, right? Not to include it in our syllabus, but it's something, it's an anomaly that we need to note. All right, because if they ask you to write electron configuration of chromium and you write it like every other element in this entire area, you are going to get it wrong. All right, so you just need to know that chromium and copper has one electron, the 4s, and then we continue. All right. Okay. So loss of electrons from 3D before 4s as well, right, has to do with electron loss from the outer orbital, electron configurations in ions, and ionization energy, as well as orbital energy, right? So what we're basically saying here, right, I won't get anybody too confused as it relates to the definition of what an orbital energy is, right? But the 3D electrons, right, are going to be leaving before the 4s electrons because of the same difference between the energy, right? If 4s is filled first, right, then the 4s is lost last, right? So it's just something like that, right? If we fill the 4s before the 3D, right, then we lose from 3D before the 4s, right? And that's something that you're going to gain through practice of writing electronic configuration, but the information is here for you guys to work with. All right?
Sorry, can you repeat what you just said a while ago, please?
What we're saying is that if the 4s is filled before the 3D, right? So if we add electrons to the 4s before the 3D, right, because of the energies, right? Ionization energy itself dictates that the 3D would actually have to lose those electrons before the 4s, right? Because we're looking at the stability of the 4s electrons versus the 3D electrons, right? Let me actually go through the slide there, right? And let me see if I can do this in a way where I don't have to define orbital energy. So when the electrons are removed from an atom, so ionization, the situation changes. Upon ionization, the energy levels of the orbitals can shift due to the changes in electron shielding and electron-electron repulsion. Right? In transition elements, the energy of the 4s orbitals becomes higher than that of the 3D orbitals, right? And this is speaking to the ionization energy, right? So the ionization energy for an electron existing in the 4s is much higher than that of an ionization energy existing in the 3D. Therefore, right, what do? We're gonna require less energy to remove the 3D orbit electrons, right, from the 3D orbitals. Therefore, 3D electrons are lost before 4s, if that makes sense. The energy required to remove a 3D electron is much lower than a 4s electron. Therefore, as we increase in energy, right, we're going to lose from 3D before 4s because 3D require less than 4s. Make sense?
Yeah, but that's not what we do.
Okay, what is that? What is it that we do?
Like when I'm doing it, the way that I
Mm-hmm.
was taught is that, or maybe me just never process what you say properly. But the way that I was taught was that even though you fill your 4s before your 3D, you remove electrons from your 4s before your 3D.
Mm-hmm.
That's what I was taught.
Okay. Mm-mm-mm-mm. All right. So let's have a look at this, right? No, that is exactly what we do, right? So what we're looking at is the information here first, right? We'll look at the first point, right? Now we're looking into the second point, right? Electrons lost from the outer orbital. Now, in ionization, electrons are typically removed from the outermost or the highest energy orbital shell, right? So that is what we're looking at first, right? So we're looking at the fact that theoretically we need to remove electrons from the 3D before the 4s, all right? But looking at how the electrons are actually lost, right? So what we're looking at is a little bit of contradiction as it relates to ionization energy versus how electrons are lost. Because in point two here, right, in ionization, right, energy electrons are typically removed from the outermost or the highest energy orbital first. As ionization occurs, the force energy increases relatively to the d orbitals, making it more stable to remove force electrons first, right? So when we're looking at the increasing in energy, right, the 4s orbitals, right, we're removing electrons from the 4s orbitals, right, lends to a more stable configuration as compared to removing from the 3D, right? So it's based off of the information here. So based on ionization energy and orbital energy, we just continue regularly, right? But we're looking at observations, the fact that we're moved from 4s first, right? That is what we're making here. We're looking at those observations there, right? So if we're looking at an electronic configuration of, let's say, iron, right? Let's get the configuration of iron up here. How many electrons does iron have? Can somebody let me know? Let's do this one. How many electrons does iron have?
26.
26 minus 18.
8.
We know why we minus 18, right?
For argon.
Or argon. So we have 8 left. So what is it that we do? We fill 4s before 3D, right? So 4s, then we fill 3D. All right. Everybody fine so far? So we're gonna have 4s2, 3D. Go ahead. Somebody saying something?
Yes, sir.
Or you're agreeing? Just hoping that you're agreeing. So 4s2, 3D, right? If we have 8 and we take with 2 already, how much we have? Okay, I think it's a weird question to ask. All right.
Is that a genuine question?
Yes, it's such an question. Listen.
Can't be the person that is going to do calculus.
LOL.
Cannot.
LOL. No, that was just a genuine question. All right, I was asking you guys that. On an actual chemistry past paper, one of the questions was 2. What's 2 plus 2? And the answer there was 4. And everybody in the Cape chemistry class turn over because of what kind of question that. And people actually get 2 plus 2 wrong. It was basically a way to give us 3 marks, and the entire question was 4 marks. So people were wondering whether or not it was a trap, but it wasn't. All right, so here now we have this configuration. Now, if we're gonna give us iron 3 plus, what would we do? Iron 3 plus would be what? What's gonna happen for iron 3 plus?
Sorry,
Sir, did you hear that question?
I'm so question repeat. I'm so confused. Repeat.
I did not hear what you asked.
I was asking now what's gonna happen for iron 3 plus. So this is iron now. What's happening for iron 3 plus?
You lose 3 electrons. You
Lovely.
lose the two forests, and then you'd have a 5 3D.
Lovely, right? So we lose now from 4. No, don't do that. Okay, so we gain here, right? And we lose in the same way, right? So that is what we're looking at. So this would be our typical iron, and this would be our iron 3 plus, our ferrous iron, different from our ferric iron, which should be 2 plus. All right. So that should be fine. Go ahead. May just confirm
Sir,
that.
isoelectronic means they have the same electronic configuration.
Oh yeah, so that's a bonus. The same electronic configuration. So what would be the? That's gonna be interesting there. Um, what the? Mm, hmm. All right, so that's interesting there. But let's see if you can find those. All right. All right, let's move on. No, I am aware that we went over the hour, but I'm giving 15 minutes more to go through the crystal field theory. Have you guys heard about this theory before?
Nope.
Sir.
No. Right. So this is a piece of information that I'm plugging into the syllabus because I don't know how they expect us to do 5.6, which is explain the formation of colored compounds and transition, well, colored compounds, right? How we get the creation of colored compounds without understanding crystal field theory. Um no, I'm just explaining something to you. You don't have to try to understand everything in its entirety, but just have a listen. All right. So, crystal field theory. An overview now. So, transition elements, we know that they are known for creating colored compounds and ions, right? We know that. That's one of the best characteristics. Now, to understand why they have colored compounds, we have to understand a little bit of crystal field theory, right? So the CFT, right, is used to explain the behavior of d orbitals when they interact with ligands. That's all it is. We're just using it for understanding why how the d orbitals behave with ligands. All right. So transition elements, metals, right? So transition metals rather have 5d orbitals, right? In a transition metal ion, right? Without the ligand itself, all of them are relatively at the same energy, right? So these electrons have the same, well, without ligands, right? So these energies, right, are the same, right? They're isoenergetic, right? And they're what we call degenerate orbitals. So you see in the orbitals that do have electrons, the empty orbitals, they tend to be at the same energy, they tend to be degenerate, right? So empty orbitals are what we call degenerate. So if you have a p orbital with empty, degenerate p orbital, all right? So it's something like that. Hydrogen would have theoretically have a degenerate p orbital. Okay? It has no electrons in the p orbital, alright? So the same thing for these now. Some of them do have some of their d orbitals filled, therefore those are degenerate. Alright? So when we interact with ligands now, right? The ligands tend to distort electron clouds around the atom, right? And it actually influences the d orbitals to split, right? So if we're looking at something like this, let me get the laser pointer. Something like this, right? When we have interaction, they tend to split and create these different orbitals now. All right, following so far? Are we following?
Yes, sir.
All right. So when ligands and those type of things interact with the degenerate orbitals, they tend to split, right? So what's happening now, right? The splitting of these orbitals, I just put this information here and put it in red because this information is a little bit much higher than, it's not much higher than CAPE information. It's a little bit higher than CAPE, right? So when we split these orbitals, right, what they do, right, is create room for energy change, right? So when the ligands interact, they donate electrons into these degenerate orbitals, creating orbitals of different energy, right? And as light energy, or as energy in the form of light interacts with the electrons and leads to photoexcitation of the electron, it will jump to a higher energy level, right? Through absorption. And then when it starts to lose that energy through emission, right, it emits a wavelength of light complementing, right, or that is quantized with the wavelength that was absorbed. Energy is quantized. So as an electron absorbs that energy, right, when it starts to emit that energy, it would emit the same energy, right? But it's going to actually be at a complementary wavelength. We have looked at this in module 1, I believe. I'm assuming that you've looked at it in module 1, not the crystal field theory, but like absorption, emission spectra of hydrogen. You should have looked at that long time, right? So you should understand that when we release energy with energy at different levels, we have different wavelengths of light. Lyman series is UV, Balmer series is visible, Paschen series is infrared. We know this, right? So what's happening with these metals is that they're releasing light in the range of the Balmer transition, releasing visible light. And that's how we get these colored compounds. Does that make sense? So what we're saying is that when the metal exists on its own, it not have no pretty color. It just silverish or grayish, or have a little tinge of a different color, right? But when that's because of all the orbitals are on the same level. But when ligands actually interact, it splits the d orbitals into different levels. And now when you have different levels, if electrons are going to transition between different energy levels, it's going to emit light. And the light at different wavelengths, that is what we perceive to be color. And that is how these transition elements produce these colors. Alright? And that is why I had to go to the crystal field theory to try to explain that, right? So the formation of the colored compounds. Here's the thing, right? The presence of these energy gaps from the crystal field theory allows electrons to move from lower d orbitals, right, to higher d orbitals. So the lower energy d orbitals to higher energy d orbitals, right? When this happens, energy is absorbed. The amount of energy absorbed corresponds with specific wavelengths of light, and the color that we perceive is the complementary color of the one that is absorbed, right? So if we have a compound that absorbs red, right, it will produce cyan, right, or that light bluish color, right? So it's similar to that of some cobalt compounds. If we absorb violet or purple light, we're going to produce a green color, such as nickel chloride, which is green. If we're going to be absorbing light blue, right, or blue-green light, we're going to produce a red color, such as ferrous iron, iron 3+. So when you look at the color of these compounds, you must be thinking about the type of color, the color that corresponds to the wavelength in which it absorbs. Ammonia is a deep blue. That means that the wavelength of light that it absorbs, that ammonia absorbs, is orange. Right? So we need to know these things. Plants are green and have different types of greenish yellows because plants, right, chlorophyll itself absorbs red light and some amount of bluish light. You guys should remember that from Unit 1 biology, because you should have spoke about chlorophyll rather, right? You should have spoke about chlorophyll and the fact that you have different types of chlorophyll, xanthophyll, and all these different types of pigments, right? And these pigments get these colors because they absorb different types of light from different wavelengths. All right. So that should be mostly it, right? So these are the factors that influence the colors now, right? Because the colors can change, yes, colors can change indeed, right? So this is how we really look at them, all right? So ligands, the different types of ligands, you have something called a weak field ligand and a strong field ligand, right? Strong field ligand tends to create deeper colors. Weak field ligands tend to present lighter colors. oxidation state as well, because the oxidation state of iron 3 plus, right? The 3 plus in iron is red, but the 2 plus in iron is, what is 2 plus? Iron 2 plus, how iron 2 plus look? What's the color?
A reddish brown, rusty brown kind of color.
2 plus? Question mark?
Is it blue?
It's a dirty green bluish color, green bluish color, actually. Iron 3 plus is red. Alright, good afternoon, Unit 2 students. Just give us a moment. Alright, the geometries as well can change the color of the complex. Because an octahedral complex different from a square planar complex, that can change the color. I'm going to talk about that in ligands, and hopefully we can do that tomorrow. Alright, so what we have left is the vanadium rainbow to get through, right? As well as using these different compounds in their different types of reactions, right? So that is the last two things. Those are the last two things, right? So we have completed objective 5 to objective 5.6. So what we have to complete tomorrow will be 5.7 to 5.10, and that will be the end of our first row transition elements. All right. So are there any questions, Unit 1? Are there any questions at all? Because tomorrow I'll have to finish this PowerPoint and then head into ligands and then complete the entire topic. All right. And I'll speak to you as to what time that would be. All right. So are there any questions for me?